Hello, and welcome to this presentation on Sonosthesia, which is a project I've been working on for a few years now, and which aims to create artistic, immersive, interactive audio-visual experiences in virtual reality. So the first thing I'm going to do is give you kind of an overview of existing software, which is related to the project in some way or another, and this will be useful to explain what the project is actually trying to achieve. So I'm going to give you some kind of background. So we're going to look at digital audio workstations and tools that go with it, like synthesizers, different plugins and audio effects. We're also going to look at different tools used in audio-visual arts, where sound and graphics are used together to produce artistic content. Tools like Max MSP and Pure Data. We're going to have a look at real-time interaction techniques, which performers use to control the artistic creation process in real time when they're performing. And finally, we're going to have a look at game engines and different types of hardware which is used nowadays to create virtual reality and augmented reality experiences. And then we'll have a look at the tools that Sonosthesia actually proposes concretely in terms of scripts and plugins and extensions and libraries, which allow these all these different types of software to communicate with each other effectively. And finally, we'll have a look at a few example applications and setups which I'm planning to work on in the near future. So to kick off, let's have a look at digital audio workstations and the different plugins that go along with them, mostly sound synthesizers and audio effects. Now, these are used mostly by musicians, composers, DJs, recording engineers, and they're used for essentially all styles of music, from electronic music to classical, jazz, whatever kind of music you can think of made using these tools. So this is what a digital audio workstation looks like. This is from Logic Pro. There are many others like Ableton Live, Pro Tools, Sonar, Reason, Fruity Loops. You can see they're very good for building structure, musical structure. You can do sequencing, you can group tracks together, orchestrating, writing scores, you can edit MIDI data and notes, control pitch bends, quantization, all stuff to do with MIDI. You can change and control tempo and loops. You can have automation tracks which control different parameters and synthesizers and effects in real time. You can add metadata to your tracks, and you can set up complicated recording sessions with lots of inputs with your sound card, and define all types of different signal flows in the software. And another thing that digital audio workstations are very good at is doing sound processing. So generally different audio tracks are presented in a channel mixer, where you can add plugins and chain them together for each different tracks in a way that's very visually intuitive and reminiscent of hardware mixers, just a lot more powerful really. And you can route different channels to buses and put different effects on those. Just loads and loads of different companies that provide plugins that are hosted by these workstations to do all kind of effects, for dynamics, compressors, EQs, reverbs, delays, flanges, And last but not least, you have a whole pile of sound synthesizers that you can plug into these workstations, and that provide you with just tons of different opportunities to make really awesome sounds, and really varied as well. You can go from the most dreamy, sweet, peaceful soundscapes with really organic feel and huge sonic detail, with constant sonic evolution. It always keeps you excited. You can spend like 10 minutes playing just one note and just without ever getting bored, really. You can have different cinematographic sound and scary ambiances for movies, nasty, mean, aggressive leads, and for drum and bass and dubsteps, and different sample databases for instruments and orchestras and choirs, and different exotic instruments for world music. There's just endless opportunities for making cool sounds. They mostly come into two different categories: sampling engines like Contact from Native Instruments, which start from recorded real-life sound sources and allow you to assign them to different keys on your keyboard and process them in different ways. And you get synthesis engines that actually create the sound from scratch using different mathematical technique. And then you get hybrids, which kind of do both, and which are very powerful, like Omnisphere. That's a synth that uses both sampling and synthesis to great effect. And you can see that the guys who make these synths take really good care to give users interfaces that allow them to have an understanding of what's going on in the synth, and how they can affect the sound and control the sound and use the synth to get a sound that they're looking for. When it comes to live performance, electronic music performers often use things like this, which are essentially fancy MIDI controllers. You get keyboards, buttons, sliders, pads that are essentially just mapped to synthesizer parameters and allow musicians to trigger sounds at different times and control parameters by moving sliders. Now they look really cool, and I've seen some pretty extraordinary performances by people who've obviously spent hours getting the best out of these interfaces, but they do feel kind of primitive in that they only allow you to control one or two parameters at once, say maybe 3 or 4 if you're using both hands, and it feels unnatural compared to, say, performing with an acoustic instrument where you're controlling potentially thousands of different parameters at the same time. Next up, audiovisual arts, which is quite a bit more obscure and academic subject, I'd say, than electronic music. It's quite a bit more technical. It's at the intersection of generative art, creative coding, computational creativity, artificial intelligence. There's many different branches of computing that are used in audiovisual arts, and the tools that are used to create content reflect the technical aspects of it. Now, it's been pretty obscure in a way. It's got a long history going back quite some time, before computers in fact, but it's really taken on a new life with the advent of fast processors and graphics cards, and it's been gaining popularity with the general public in some digital arts festival in recent years, and it's really given birth to a new generation of full-blown audio-visual artists. They're still quite rare, but there are definitely quite a few people out there making some really interesting and aesthetically pleasing stuff, and making work where the audio and the visuals don't make sense without each other. They really work together in a symbiotic way. So what are the tools that people use to make these things? Basically, it's divided in two categories. There's actual programming languages and libraries like processing and open frameworks, which are basically coding environments. You code the maths of the content, so you really need a deep understanding. There's another breed of software which is more hybrid and slightly less technical, but still pretty technical, which are the visual programming languages like Max and Pure Data. So in these types of environments, you create patches. This is a typical Max patch. You can see it can get quite hairy and disturbingly complicated. Essentially works by connecting objects together, and objects act as sort of self-contained programs, each of which receive inputs and generate outputs. So it's a lot lower level in a way than a digital audio workstation. So everything happens in real time, and through these outlets and inlets, there are the different types of messages that go through. You get actual data, control information, integers, floats, symbols, triggers, and then you get actual signals like audio data, which is a lot higher frequency, and you can also get multi-dimensional signals to encode video or other types of media. Now, using these control flows, you can quite intuitively create cross-domain control flows between audio and graphics, and use one to control the other, which is something that's very hard to do in any other way. So now I'm going to talk about an important aspect of audio-visual arts, and that's real-time interaction. So performers need ways to control their content in real time, and that's especially important in the context of live performance, where the audience needs to feel that the performer is really controlling the content and having an effect, and this is vital to create really engaging performances. Now, with the advent of touch screens, relatively cheap touch screens, like on tablets, there's been the opportunity to create fully customizable interfaces with sliders and buttons and touchpads. Now, taking the concept further, there's been quite a lot of work done on tangible interfaces with things like the React table, which is a large horizontal backlit display and allows people to place blocks on the table, and each block represents a different musical creation element, like an oscillator or an LFO or a sequencer or a periodic trigger or some scale modifier or some aspect of musical creation. And so this creates a really cool platform for experimenting and collaborating and live performance. Another aspect of real-time interaction is gestural control, where the performer's gestures are captured in some way, and that's used as an input to control different elements of the musical or graphical performance. A particularly good example of that is Imogen Heap's performance at TED, where she performs one of her songs both singing and controlling different electronic instruments using the gloves. You also have a number of camera-based capture devices like the Kinect or the Leap Motion that have been used in a number of ways to control music or graphical performance. This, for example, is the Asphyxia Dance project, where the movements of a dancer are captured and used to control procedural graphics in real time to great effect, I think. Now, one of the problems with these gestural control devices is that they generate huge amounts of data, which is good, but it's then very tricky to map this data to audiovisual synthesis parameters in a way that's intuitive and powerful. And one of the reasons for this is that the gestures are made mostly without context. That is, the gestures are made in empty space without any relation to objects, which is quite unnatural for us. We don't expect in the real world for our gestures to have any effect unless we're touching something or interacting with something. So, for example, a drummer will learn some drum strokes and some patterns, and will then be able to reuse the same strokes on different places in the drum kit, and will be able to use the same gestures to radically different effects depending on where in his environment he's performing them. So in my opinion, it's really crucially important, if we want to have really effective gestural interfaces, to find a way to add context to the gestures of performers. And this is where VR comes in. Now, virtual reality, or VR, has been coming for a while. It's taking a lot of time to take off, and one of the reasons for this is that it's technically very difficult to do. But it's here now, and you can get things like this. Like this is the HTC Vive. It's got a headset and two controllers, and they're tracked pretty accurately by this lighthouse system, which are the two cubes you can see. And it works really well. I mean, if anyone hasn't tried it yet, please do. It's really quite an experience. And there's app stores now like Steam that allow the game developers to publish their VR apps and users to download them and play them on their device. And it's really taking off. And there's lots of other products. All the big tech companies are investing huge amounts of money in trying to be the first to get VR right. Got HTC, PlayStation VR. Google's doing loads in terms of bringing a VR platform with Daydream and Tango. Samsung's got their Gear VR headset, which allow you to do some kind of cheap VR with your mobile phone. And Microsoft is on board with the HoloLens for an augmented reality experience, which is really quite impressive as well. Apple are taking their sweet time, but we can expect them to enter the market with some pretty cool, if overpriced, augmented reality device pretty soon, I would expect. And so what do developers use to make applications for these devices? Well, there are pretty much only two options. There's Unity or Unreal, which are two game engines. And they've both been really investing heavily in VR, and they are very, very powerful. So first they target a very large number of platforms. So basically you develop the project once, and then you can run it on anything. So mobile, web, consoles, desktop, and obviously most importantly for the project, VR and AR. And there's full-blown programming environments. So game developers just have a hybrid environment where they can both edit their scene in 3D and import assets, and have the coding side as well, where they can define behaviors of their objects in code from the programming environment. They also have a very high compatibility with files exported from 3D modeling and animation software like 3D Max, Maya, Blender and Lightwave, and very powerful physics engine, which is extremely important for VR, but also very interesting for the project. It's very important to be able to detect collisions between objects, or to model the virtual world in a physically realistic way, with collisions and joints and friction, rigid and soft bodies, forces and fields, and etc. Another thing that's really amazing is they have huge asset stores where you can get tons of really interesting stuff, ranging from libraries that implement certain types of behaviors, graphical assets, meshes, models, animations, and just loads of stuff that are relevant to games, but also to VR, and available really easily from the environment. You can just go to the asset store from within the editor, search for things, and download them and import them directly into the project. And last but not least, there's quite a few procedural graphics and procedural sound generators like Houdini, Popcorn FX, Wise, and Fmod that have plugins for Unity and Unreal, so that developers can use the content that's created with these external software packages and use them within Unity in a very effective way. Okay, so we've got all these really cool features from VR game engines, but how can we use these in the context of interactive audiovisual arts? Well, the first thing we can do is have interaction in context, as in we can interact with the virtual environment as if it's the real world by touching objects, by tapping, scraping, scratching, pinching objects. All these controllers that are coming out are getting more and more sophisticated and allowing very intricate object manipulation in virtual reality. So we can use that as a very powerful input device. The other thing it allows us to do is to have completely configurable input control objects, the objects that the performer would manipulate to control things. They can have any shape, any color, any texture, any kind of behavior or dynamics that we wish, just because of the fact that they're virtual and that we can control them completely. And we can use this in order to give visual cues to the performer as to how objects will react in certain conditions when the performer will touch the objects. An analogy in the real world would be that when we hit a glass bottle or a bit of wood or a tambourine or whatever object, we have some expectation as to what the resulting sound would be. Even though we're performing the same gesture, the fact that we're performing it on a different object with different visual characteristics gives us some understanding before performing the gesture of what the sonic output would be. Now, another important thing is that we have a physics engine, like a full-blown physics engine at our disposal within the VR environment. This comes for free with Unity or Unreal or any game engine, really. And this is very powerful because it allows us to understand forces and pressures and frictions and joints, and use that as a input information to control visuals or graphics. So this kind of replaces the traditional electronic music input device that has mechanical sensors like buttons or sliders or air pressure sensors. Here we've got a way of having any number of sensors within the world for free, just by acquiring information from the physics engine. You can also use physics as an artistic tool in itself by controlling the scene to create visual effects that are aesthetically pleasing, by inserting turbulences in particle systems or fracturing meshes or controlling fluid dynamics. There's a whole area of procedural arts which is quite difficult to get into because you need a good understanding of the physics engine, but it can be used to really great effect. Now, there's also a really big multiplayer tradition in game engines, and Unity and Unreal reflect that by giving developers very good networking tools, which gives a really good opportunity to create collaborative environments in the context of audiovisual arts. So you can have avatars of several performers in the virtual environment. This can also be extended to the audience, so you can also have the audience each have their own VR headset and be immersed in the performance environment and seeing the performer evolve and actually create the content in real time and be fully immersed in it. And the last point I wanted to make is that you can have scripted immersive tutorials, which is a quite widespread technique in VR games, given it's such a new medium. The first steps when a new user starts playing the game is to actually teach the user how to use the controller, in what way it can interact with the environment, and what it can do. And this can be really useful to teach new potential users how to use the system and allow them to become really effective quickly and spread the word in a way. So now on to the meat of the presentation. We've had a pretty long overview of the different types of software that Sonosthesia wants to interact with. Firstly, there's digital audio workstations, which are used heavily in the music industry and are very good at building musical structure, organizing sound, scores, orchestrating, creating different sound processing paths, channel mixing. There's tons and tons of commercial libraries and synths, and there's a huge user base of really talented electronic music producers and musicians that are very experienced using these tools. Next, there's audiovisual programming environments like Max or Pure Data, which have a lot more low-level technical event data flow approach to content creation. They're very good at creating cross-domain mappings between graphics and sound. They have a very active tech art community and lots of academic published works using these tools, and it's just a very big resource for audiovisual arts that it would be a shame not to tap into. And lastly, there's VR and AR engines like Unity and Unreal, which have massively multi-platform capabilities. They have lots of ways of abstracting control input, rendering and tracking for different platforms. They offer lots of opportunities for visual arts in terms of contextual immersive interaction. They have physics engines that are really powerful. They have huge asset stores, and the whole heritage of the gaming industry that's been going on before VR, and now an exploding user base that are using different VR headsets. And as VR is really taking off, these engines become more and more important. And so all of these tools are relevant in some way or another to digital arts, and as a very complex multidisciplinary subject, which allow for a great diversity of skills and talents to express themselves. And these tools are very different in many ways, and they guide content creation in different ways. Some are lower levels, some are higher levels, some are visual, some are code-based, some focus more on music, some focus more on graphics or interaction, and they all have different relative strengths and different aspects of functionality, and they're all relevant to the project in some way or another. So it would be nice if we could merge them together, but the fact is they're very different, and they are very incompatible in many ways. It's very difficult to get them to talk to each other and exchange information usefully in real time, so that they can interact with each other. So that's where the project comes in. So before I go into more detail about the protocol used by Sonosthesia, I'd like to give a quick description of existing communication protocols and why I didn't find them suitable for the project. So the first one is MIDI, which is the musical instrument digital interface, which was introduced in 1980, I think, for the classic Roland TR-808. So it's an ancient protocol, and so it's been around for nearly 40 years, and it's remained remarkably unchanged since the beginning. It's very specific to music. It's not really used in any other industry, and that's because the musical semantics are encoded in the data. So you get things like note starts and stops, pitch and velocity, different control signals for music-specific parameters like volume, vibrato, panning. You get clock signals to set and synchronize tempo between devices and send start, stop, record signals to different software. It's also very coarse and limited in many ways. It's you can only have 16 different channels of instrumental data. You can only have 127 values for pitch or velocity or other control signals, although there's some hacky ways of getting more out of it. There have been some few extensions like GM2, machine control, polyphonic expression that have kind of expanded the possibilities somewhat. And also there has been some improvements in the connectivity. That before you could only use MIDI cables, now you can use Ethernet wireless or other ways of connecting MIDI which are more convenient. But overall it remains pretty limited and domain specific. Then there's the Open Sound Control Protocol, which was kind of designed as an alternative to MIDI, where higher resolution and richer parameter sets were required. So the objective was really to overcome some of the shortcomings of MIDI when controlling synths and computers and multimedia devices on a network. And it's definitely succeeded in terms of flexibility and accuracy. It's also meant that it's somewhat less widespread than MIDI, because the fact that it's got no fixed semantics means that it's more difficult for hardware and software manufacturers to understand each other and have some kind of common way of speaking to each other when it comes to musical control. So it's more difficult to use OSE in order to control synths or effects with input devices. But it's definitely more flexible and powerful than MIDI. It's also got its limitation when it comes to data representation. An OSE message is basically an address that defines what the control is meant to control, and then a series of arguments which can be strings or ints or floats or a number of other things, but there isn't any way of representing complex nested structured data other than sending a binary blob, which removes some of the semantics in the protocol. It's also got that same problem as MIDI in that it's unidirectional. So basically you have OSE servers that expect messages to be incoming, and you have clients that send control data to the servers, and the servers just obey these control messages, or at least they're meant to, and they're not meant to talk back to the clients. You're not meant to have some kind of request response either. It's just clients sending control data to servers. Now, another approach to communication between different components that's been used in a number of different domains, including audiovisual arts, is MultiAge Communication, which is a very broad subject, and it really encompasses many different libraries and approaches and environments, and it's a lot less specific than MIDI or OSE. It's more of a philosophy, but it's one that I think is very useful for the project. So the basic idea is that it supports the coordination and the collaboration between different agents, and the agents declare what are referred to as percepts and actions, basically inputs and outputs, and all the agents are at least partially independent, self-aware and autonomous, and they don't have a full global view of the system. Each agent just knows about what the inputs and outputs are, and they then interact by affecting and being affected by an environment which can be modeled in many different ways. So I just wanted to mention this because it's really informed the protocol used by Sonosthesia in many ways, although Sonosthesia just uses a very small subset, because multi-agent communication just covers a huge amount of different possible scenarios which we're not really interested in the context of the project. So just to clarify a bit of terminology that I'm going to be using, I'm going to spend a bit of time actually explicitly stating what I mean. So a parameter is a variable which can be a scalar or an n-dimensional vector. In MIDI, a parameter would be like pitch or velocity or panning or anything that you could think of it in MIDI that's controlled numerically. Then channels are essentially keyed parameter set. So a channel in the context of MIDI can be like bass or guitar or drums or something. It's just that in the context of Sonosthesia, the parameters aren't fixed. A channel describes its own parameters. It says I can control this or that, and it's not fixed to being what MIDI describes. It can describe anything. Now a quick note on channels is that components can have incoming or outgoing channels. Now an incoming channel to a component can be used to control that component in some way, and an outgoing channel can be used for the component to describe some aspect of its internal product. Then instances. Now instances are dynamic objects created and destroyed by channels. In the context of MIDI, that would be notes, for example. So the idea is that you can create note instances, and then each note can have its own has its own instantiated parameter set, which can be controlled independently. So you can create a new note, and then in theory you could change its pitch or its volume independently from other notes on the same channel. And then components are just a static grouping of channels that can be declared on the network. And another thing to note is that channels can be both static or dynamic. A static channel doesn't create instances. It just offers a parameter set which can be controlled. A dynamic channel is used to create instances, and then you control the parameter sets of each instance of the channel separately. So now I'm going to actually describe what the different types of messages supported by the protocol are. I'm going to be representing the data as JSON, which is hopefully quite intuitive, but if you don't understand what's going on, you can have a look at what JSON is and how it expresses data. So the first type of message is a create message, which creates an instance on a channel. So it's got a type property which defines it as a create message. It's got a component and a channel property which describes which channel in which component it relates to. It's got an instance property which is like a globally unique identifier, which allows subsequent messages to define which instance they're referring to. And And then it's got a parameters property, which is just a keyed dictionary with a value for each parameter. The value can be either one numerical value or an array of numerical values. Then you have control messages, which essentially just updates parameter values for a given instance on a channel. So here the component and channel properties are actually redundant because given the instance identifier is unique, the system can determine what channel and component the instance belongs to, and then just an updated set of parameter values. And then there's the destroy message, which destroys an instance on a channel. So this is like a MIDI note off, if you will. And you can specify a set of final parameter values if that's useful in some way. So I'm going to give you a more concrete example, which hopefully will be more relatable. So if you imagine a digital audio workstation, which can be thought of as a component in the sense of Sonosthesia, and imagine you have a synth, like I've called it pad 2, just arbitrarily. Now this synth is essentially like a MIDI controllable synth, where you would traditionally send MIDI notes on and off, and then each note would have a pitch and a velocity, etc. Now, in terms of Sonosthesia, this is an incoming dynamic channel. So imagine we want to play a new note on that pad, then we would send the equivalent of a note on message, which would be a create message. So that create message, it has a target channel, which is pad 2, which allows whatever implementation there is to understand what it's meant to control. It's got an instance key and a set of parameter values. So this is the equivalent of a note on message. Then if we want to say control the pitch to perform what would be in MIDI terms a pitch bend, then we can update parameter values by sending control messages. And then when we want to turn the note off, like the equivalent of a MIDI note off message, we would send a destroy message, which refers to that instance and has some parameter which can be useful for this destruction. In this case, it's a release parameter which describes how quickly the note should fade away. And then imagine that in this digital audio workstation, there's some channel with audio on it with a bass instrument, and this channel wants to send data out that describes audio parameters for this channel. So this would be referred to as an outgoing static channel in terms of Sonosthesia. What happens is just that you have a plugin on the channel in the digital audio workstation that analyzes the data and sends Sonosthesia messages out to the network. There's the multi-dimensional parameters that come into play. For example, for describing spectral bins, you don't necessarily want to commit to a specific number of bins. This can be handled dynamically, and so we want to have the parameter expressed as an array rather than as a one scalar value. So now imagine that we have another software component, in this case a VR simulation running in Unity possibly, that exposes a different set of channels with different parameters. So in this case I've got an outgoing dynamic channel which represents a sphere and interaction with this sphere in terms of contacts and collisions with it. And essentially a new instance is generated every time an object comes into contact with that sphere and lasts for the duration of the contact. And there's another incoming static channel which is used, for example, to control the hue or emission densities or swirl of a particle system, say. Now what we'd like to do is, for example, to take one outgoing channel from the VR component and map it to a component in the digital audio workstation, so that, for example, when something comes into contact with this sphere, it creates a note in the digital audio workstation. Another possibility would be to take the audio analysis coming from the bass channel in the digital audio workstation and use that to control the particle system. Now the problem with this is that although we have the same semantics, we don't have the same parameters. So there's an incompatibility here. You can't just take one channel and feed it straight into another. We need to somehow map the parameters, one parameter space to another for it to become interesting. So my original approach to this was for in each case having an interface for specifying the parameter mapping, and I was finding myself re-implementing an interface which is actually quite complicated in each of the different environments where I wanted to create components. I needed an interface for the digital audio workstation to specify its parameter mappings. I needed an interface in Unity. I needed an interface in Max. And so I came to the conclusion that it was better for components to just have inputs and outputs and not worry about who it was talking to or where it was getting its messages from, which is where the hub comes in. Now the hub is a special bit of software, a software brick, which isn't a component. Rather, it's meant to act as an environment in the multi-agent communication context. In other words, it's used to map outgoing channels to incoming channels and to create mappings between the different parameter spaces so that you can get a compatibility between different channels. And so the idea is that you create, control and destroy messages, transit through this hub. The parameter space is mapped, and the messages are then just relayed from one channel to another, so that you can have anything control anything, independent of how heterogeneous the systems are. As long as you define a parameter mapping, then and a way of describing your system in terms of static and dynamic incoming or outgoing channels, then anything can control anything else. So the last message type is the component declaration. So this is perhaps the most complicated in terms of data structure. So I'm going to go straight to concrete examples. So this message goes from the components to the hub, so that the components can declare the channels and the parameter set for each channel to the hub. For example, here we have a VR component declaration which has two channels. So the first channel is identified as sphere 1. It's got a flow that's emitter, which means it's an output channel which emits descriptive information about the system. It's got 5 parameters which describe the different aspects of the collisions with the sphere, so how hard the collision is, what the angle of incidence is, and the texture and material of the sphere at the point of collision. And so the second channel has identifier Win2. It's defined as a receiver, which means that it receives control information from the outside, and its parameter set is described as an array of objects rather than an array of strings. This is You have a choice. The array of strings offers less meta information about the parameters. So in this case, you can define for each parameter an identifier. You can define the dimensionality of the parameter. If you remember, it can be a scalar or a vector of any dimension. So in this case, it's the first parameter has dimensionality 3 to define a three-dimensional vector in 3D space, and you can give it a default value. So just a quick recap of the wider picture. Imagine we have a software component, component 1, that declares an output channel which has parameters 1, 2, 3, and 4. And this output channel is used to send descriptive information about its own state to the environment. We then have component 2, which has an input channel, and as an input channel, this allows the control information to be sent from the outside into the component, and this input channel has parameters 5, 6, 7, and 8. And so we have on one side an output channel, and on the other side an input channel, and they have mismatched parameters. So the idea is that component 1 and component 2 don't need to know about each other. Instead, what they do is that they declare their channels to the central hub, and then we can use the hub in order to create mappings from one output channel to another input channel. And we then need to reconcile the two distinct parameter sets, and this is done in the interface of the hub, so that we don't need to replicate this complicated mapping interface in each different kind of environment or GUI toolkit or whatever. We have one program whose job it is to create mappings, and then we connect components to it, and then each component only worries about its input and output channels, and doesn't worry about which other components are on the network. Okay, so now that we've got a better understanding of what the Sonosthesia is actually trying to do, I'm going to give you an overview of the tools that I've been developing towards this goal. So the first one is the Sonosthesia Analyser, which is basically an audio plugin for sound analysis. So the idea is that you can use it as a plugin on audio channels in any digital audio workstation or any other kind of software that can host audio plugins. And unlike most other audio plugins, the idea is not to change or process the sound, it's to analyze the sound and then send the data, the analysis data on the network using the Sonosthesia protocol. So this project was in fact forked from the sound analyzer by Adam Stark. I did some research when starting work on this, and I realized that there was already this project that did mostly what we needed. I just changed it quite heavily in terms of how it communicated the analysis information on the network, so it was more compatible with the Sonosthesia project. But in terms of audio analysis, it really does everything we need. It uses the GIST library, which offers a whole load of different audio analysis options like RMS, zero crossing rate, spectral differences, spectral centroid, loads of different time and frequency domain features, onset detection, pitch detection, etc., etc. And so it was very useful in a big head start for that project. And it runs on Juice, which is essentially the Unity for audio plugins. You write the code once, and then you can target a load of different types of audio plugin protocols like VST, VST3, audio units, AAX, etc. So the next project is the Sonosthesia Relay, which is very similar, in fact, to the analyzer. It's the same idea. It's an audio plugin based on the Juice framework, which you can use in any host application which will handle audio plugins. And the difference is that instead of transmitting audio analysis data on the network, it will transmit the MIDI either notes or control data, or the automation data on the track. And this is very useful because it gives us access to the raw information that was used to create the music, and it's often better to use that than to try and extract, pitch and other types of things. It also allows us to actually create just data within the workstation that isn't actually used to generate audio, but just used to create control signals that are associated with the sound, but that just describe some kind of perceived impression about the sound. So if, for example, you could create a darkness or some kind of descriptive information on the sound which wouldn't be extractable, but just you feel about the ambience or the general sonic environment, and you could offer that as meta information on the music and use that as control signals to control something else. So then there's the Unity aspect of the project, which in a way is a lot more messy and complicated than the two previous projects I've been talking about. So firstly, I've been working on kind of the core elements, like the networking between Unity and the hub, and different ways of declaring input and output channels as game objects, describing channels and their parameters, and then having ways of having other game objects subscribe to this channel to receive objects or push messages to outgoing channels. I've been doing my best to try and make these things reusable and generic enough to be useful in a wide variety of situations. I've also been working on different generators, modifiers and descriptors that use these messages to affect the scene in some way by creating objects, by modifying textures and shapes and colors and forces, to allow the incoming messages to affect the scene in some way. I've also been working on interaction descriptors, which are meant to allow the user to use the virtual environment as an input device by, for example, using the collision data between virtual versions of the hands with objects in the virtual environment to create control signals to control whatever. Another thing I've been working on is trying to provide ways of controlling procedural plugins that are available for Unity and which allow different types of external software packages which are very good at procedurally creating content for Unity, like Popcorn Effects, Substance, Wise, Fmod. There's many different tools that offer plugins that can then run in the Unity game engine and be controlled in real time. And I'm looking for ways to allow the Sonosthesia messaging and input and output channel model to be compatible with those by linking them in some way. And last but not least, the hub. Now I spent some time wondering what tools to use to develop this program, and so I was looking for something that was very cross-platform, at least running on Windows, Mac, Linux, that was free and open source and very versatile, could adapt to a lot of different scenarios, because maybe the hub will have additional parts of functionality in the future, other than creating mappings. And it needed to have very strong networking and very strong UI tools. So keeping this in mind, I chose to use Node.js for the networking, because, to be honest, I've worked with a number of networking technologies, and Node is the best in my opinion. It's got an unusual asynchronous callback based programming model, which is extremely well suited to networking, and it's got really fast performance. It's also got a very large ecosystem of open source libraries available through the Node package manager. Now the question is, how do we add UI on top of Node? And the general approach to this is to combine it in some way with Chromium. Now, both have an API in JavaScript, but they're different runtimes, and there are tools to combine them, like Electron and Node WebKit. But the advantage of using Chromium is that it opens the door to tons and tons of front-end web UI frameworks, most notably Angular, which I've been very impressed by. And so together, I think Node and Chromium and all the networking tools offered by Node and the different UI options given by Chromium offer a really great sort of compromise between networking, UI, and cross-platform. So the project is well on the way. It's still very much alpha. The core networking and messaging and mapping functionality is there, but there's lots of things missing in terms of user experience and saving sessions, and the UI is still pretty ugly, and I'd like to work more on that, but it's pretty close to being functional. So the last thing I'd like to do is talk about a few example setups and applications that I have in mind to work on in the near future, using the tools that have been developed for the project. So the first thing I'd like to do is to use a VR application as a control input for traditional musical software setup, using some kind of digital audio workstation like Ableton or Logic, and synths that are plugged into the audio workstations with different channels set up with plugins and effects. The traditional live electronic musician setup. So if you imagine that we have a Unity app where we have the VR user using controllers interacting with its virtual environment by touching objects. Now you could touch objects just by using the controllers and the colliders on the controllers. You can also have some kind of expanded, controller extensions, like you would use a bow to play a violin, for example, and then you can use the buttons on the controller to control these extensions of the controller to interact with the objects in the scene in a more powerful way. And so if you imagine that these objects in the scene are configured to send control messages, they create an instance on a given output channel whenever there's some contact made with the object, then this information goes through the hub. It's mapped in some way to the synths in Ableton, and then this information is forwarded through the channel mapping and creates some kind of sound by controlling a synth or modifying a parameter or whatever you fancy. And then in Ableton we have the plugins like the Relay and the analysis plugins that analyze the sound that's generated and then provide feedback information on the sound that's been generated to the hub, and then that's mapped back into the Unity environment somehow to control the scene. And in this way you can control anything you want in the scene, as we've discussed earlier. You could control particle systems, colors, textures, forces, wind, whatever. And in this way, you've got a really cool bi-directional interaction going between the two sets of software. Another cool possible application is to augment the traditional performance setup used by musicians by providing a virtual reality layer, an augmented reality layer on top of the real world, which allows performers to not be completely cut off from their traditional performance environment and have to perform entirely in a virtual reality app. They can instead have the best of both worlds as far as they're concerned, and have an augmented reality environment on top of their traditional setup. And so in the same way as before, use 3D virtual objects to send control signals to synths and effects units, and also produce amazing visuals in the same breath. And the cool thing about Unity is that it's got a very good multiplayer architecture, which means that, for example, if you have an audience that's looking at the performer in his augmented reality setup, you could easily provide augmented reality glasses to the audience, and they have the version of the application running, and they can see the augmented layer used by the performer, so that they're not just looking at some performer waving his hands about in empty space. They can have an idea of the context of the performance, and also have access to the amazing procedural graphics going on at the same time. So I hope I've succeeded in convincing you that this is a project worth working on. There are just tons of possibilities I haven't talked about, and the idea is that really we have a really extendable platform that can give artists from loads of different backgrounds and skills and using different software the opportunity to collaborate together to create new types of audio-visual arts that are really immersive and interactive. So if you're interested, please get in touch. I want as many people as possible to get involved with the project, whether it's on the technical side or the artistic side. I'm looking for sound designers, for musicians, for 3D effects or animation artists, tech artists, audio-visual arts people, web developers, you name it. Anyone who feels related in some way to what's being said here is very welcome to get in touch and get involved. Also, companies who might want to invest in the project, I'm looking for ways to spend more time working on this and perhaps making it full time. So please get in touch, and I hope to hear from you soon.